Hi and welcome to John's Maths Book. In this video, we're going to be proving the fundamental theorem of calculus, part 1. If you like the video, then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. The fundamental theorem of calculus links together differential and integral calculus. Let's take a look at what the theorem says. So it says if f of t is a continuous function defined on the interval a comma b and capital F of x is the integral from a to x of f of t dt, then the derivative of capital F of x is equal to f of x. I've drawn the function f of t on the whiteboard and marked points a and b on the t-axis. Between points a and b, I've marked in point x. The green shaded area is the area under the curve determined by the function capital F of x. This function will return the area under the curve for any value of x between a and b. So for any given value of x between a and b, if I plug a value of x into capital F of x, it will return the area under the curve for that value of x. What we know is that capital F of x is equal to the integral between a and x of f of t dt. And what we're going to try and prove is that f prime of x, or df by dx, is equal to f of x. If we now take a look at the derivative of capital F of x from first principles, it's given as the limit as h approaches 0 of capital F of x plus h minus capital F of x, and this is all divided by h. If we examine the numerator, graphically, capital F of x plus h is shown in the diagram at the top left, and capital F of x is shown in the diagram at the bottom left. If we now subtract these areas, we are left with the area shown here shaded in green. If we now examine this green shaded area, we see that to calculate it, it's equivalent to the integral from x to x plus h of f of t by dt. So we can now rewrite the derivative of capital F of x to include this integral. If we now apply the mean value theorem for integrals to this area, we know that there's a point C between x and x plus h where the area of the rectangle created when we multiply f of c by h is equivalent to the area enclosed by the curve or the green shaded area here. As you can see, I've extended the green shaded area to include the rectangle created, which has a height of f of c and a width of h. If we now replace the integral with f of c times h, and we eliminate the value of h from the denominator and the numerator, we're left with the derivative of capital F of x is equal to the limit as h approaches 0 of f of c. Now we need to look at what happens in the limit as h approaches 0 of f of c. Here we need to remember that as h approaches 0, it also approaches x. And at 0, it is x. So to look at the effect on c when h approaches 0, we can make use of the squeeze theorem. Now, as h approaches 0 and therefore x, c does the same. And therefore f of c approaches f of x. So the limit as h approaches 0 of f of c is f of x, and the derivative of capital F of x is therefore f of x. So now let's look at a problem to see how we can apply this. So let's take the derivative with respect to x of the integral between 0 and x of the square root of t squared plus 3 dt. Now from our theorem, we know what the answer is. It's the square root of x squared plus 3. But let's work through the problem to see if we get the same result. So in this example, f of t is equal to the square root of t squared plus 3. So now we want to find the derivative with respect to x of the integral from 0 to x of f of t. Now we know that the integral from 0 to x of small f of t is capital F of t. So we can evaluate capital F of t between the limits of 0 and x. So if we evaluate capital F of t between these limits, we're left with capital F of x minus capital F of 0. and we want to take the derivative of the resulting expression. So the derivative of capital F of 0 is going to be 0 because it's a constant. So we're left with the derivative of capital F of x, which we know is lowercase f of x. Now, as we saw, f of t is equal to the square root of t squared plus 3. So therefore, f of x is equal to the square root of x squared plus 3.